Okay, hi guys. So basically, we're just talking about light first. So we may have heard many stories about light. It's been around for a long time. So things that in the context of light, when people studied it, they didn't think like, okay, this will be one day relevant to quantum mechanics. Yeah. So some introductions of some ideas of how they conceived of light in the past. So if you recall high school physics, there's a decent chance you probably heard that. Okay, light just travels in straight lines. You draw them as nice little rays. Light is good and easy. Then, so how light changes and stuff, it's basically a very simple problem. So slightly sidetracked, but it's a typical lifeguard problem where let's say you're the lifeguard on the beach, there's a victim in the sea, and like, okay, that guy is clearly drowning, I need to go save him. And okay, so your intuition is, I need to get to the victim in the shortest possible amount of time. Okay, what's your intuition going to tell you? Like, how do I get to the person in the shortest amount of time on a flat piece of land or something? Yeah. So basically just, okay, let me just run in a straight line and then basically get to the person and save them. So the slight complication here, when you're on the sand and you're in the water, move at different speeds. Like you find it faster than you swim. So now suddenly like, okay, do I get the shortest amount of time? So any thoughts? I mean, it's a very relevant problem, right? If you ever go for lifeguard exam, right?
It's like a light example.
Oh yes, we're getting there, don't we? But the basic idea is that okay, yes, yeah, I'm getting okay, really, everyone's really jumping into on this. So what you can think about is that okay, if I'm on the sand, I know the answer is a straight line. If I'm in the water, the answer is always a straight line. So alright, so let's just plan like say some boundaries first. So you can say, okay, if I'm on the sand, right, if I want to get to the water in the shortest possible amount of time, I just run in a straight line. Okay, if I'm in the water, if I want to reach the land in the shortest possible amount of time, I draw another straight line. So as you can see, you can have this like nice little parallelogram to kind of demarcate your possible choices. So you now reinterpret the problem and say, okay, since I know what the answer is on sand and in the water, why don't I just find where do I need to cross the boundary, so to speak? So from this little setup and parallelogram, you kind of guess that, okay, it has to occur somewhere within this region. And then you can kind of use your intuition and tell that, okay, since I run faster on the land, I should maybe spend a bit more time, cover more distance on the land before I hit the water. So you see like, okay, there's this midpoint over here. So maybe like, if I run faster than I swim, maybe I should cut the water somewhere around this region. Whereas if you happen to swim faster than you run, if you're a fish, for example, then maybe you might want to cut into the water like around here instead. Everyone make sense? Okay. So again, this is where you jump into the straight idea of light, whereby, okay, this is basically just light in essence, or you might have heard of it. So you can call this one an angle of incidence, an angle of refraction. And like, okay, then you just basically put in the math, you have sine of the theta incidence and divide by sine theta refraction, just the ratio of your running speeds or your swimming speeds in this case. Then you just move things around, very simple. And now you just define something called a refractive index, or I guess there's a ratio of your running speed in a couple of directions in space. So another simplification here is that because the electric and magnetic fields, they are always related in free space. So you just need to pick one and you basically know how the other behaves. So most of the time we just concern ourselves with the electric field, since it's usually the stronger of the two components. So when I say that light or is waving in a particular direction, I mean the electric field. And it's just implied the magnetic field will just do what it does because from Maxwell's equations. Okay, so as Peter mentioned, you can have this what you call horizontal and vertical polarizations because of how it wiggles. So you just get comfortable with math. Your E just stands for electric field, A just means your amplitude, your cosine equals well with a sinusoidal wave. Then the other important terms like omega is just angular frequency, and your phase is right here. So another assumption is that, as you can see, the direction of propagation is basically your z-axis. So anytime I say light propagating, it just assumes that it's propagating in the z-axis, and so we only have to worry about, say, x and y. So things that there's more than that to light, like it can do that. So Sheikh, help me out. Sure. So these are the fun parts. You have nice ropes. You can please. Thank you. Yep. Okay. So okay, Sheikh, you can just move back a little bit. Yep. Okay, so basically the whole idea is that can anyone see the rope? Yeah, okay, we're just gonna have some fun over here. So basically, it's just that Sheikh, just try moving the rope. Like, how many ways can you move the rope around?
Oh, that's one.
Yeah, that's one.
Right.
Okay.
I can also move it like this.
Yep. In principle, yes.
True.
But
Or I can
try
even
describing them.
like this. Right? So I can either have it this way, or some combination of both, which kind of looks a bit like that.
But I want to do sideways too, man.
Yeah. Front and back, like this.
Yeah.
That's a
That
bit
doesn't
trickier.
what? Wait, let me just think.
As a material wave,
Okay, yeah.
perhaps. As a material wave, perhaps, but maybe for not for light. But if I want to do it sideways, that also works.
I think that kind of wave, probably if you have a spring or something, maybe you'll be able to see it a bit better. But yeah,
Yep.
that is valid as well. Kind of.
Right. So basically, when there's new property or something, people like physicists are just like, okay, well, you get paid to go find out about how these things behave. So the problem then is that you want to describe all the possible polarizations. So as you've seen from Sheikh's example, is that you can wiggle your rope or wiggle your light in many different weird shapes and forms. So one way of like describing it is like, okay, how does this look to me? So for example, if Sheikh is sending me the little wiggles of the rope, I'm just gonna look and like, okay, on my end, I can see what kind of path it traces out. Does it go in a line? It makes a shape. So in general, you can get some kind of weird ellipse or this thing. So it's like basically just the shape that it traces out as you see it coming towards you, for example. So if some orientation angle, it just says, okay, how bent or rotated is it? And then there's some elasticity, obviously how stretched or how compressed this thing is. So it may look a bit complicated, but if you recall, hopefully people will have seen this expression back in like high school or secondary school. You guys should know what this equation is, right? Okay, so as in just an equation of a circle. So the whole idea is just like, okay, the cos of the ellipse rotation is basically this term. So if you recall the phase term I denote as phi, in this case, the phase difference between your x and y axes in there. So this is just a quick overview whereby I just say, okay, these all bunch of parameters, and this I can describe all kinds of shapes and all kinds of polarizations. And okay, life is good, it's problem solved. But then again, not quite. For example, polarizations can change, when from one source to another. And then how handy is it if you have this description like, okay, I have this thing, it squashes the polarization ellipse in this way, or I have this thing, it stretches it in some way. Not a very, I guess, easy formalism to work with, right? Okay. Maybe I need to convince that it's not so easy to work with another time. Okay, new tutorial problem next year. You need to convince the students how this is a very bad system to work with. Okay. So let's just consider some special cases first. So in physics, one of the tricks is that if something looks complicated, you try subbing in certain values that make your life easy. One of those values happens to be 0. When some things are 0, many things disappear and your life gets simple. So for example, in this case, I can consider that if the electric field in the y direction is 0, then okay, everything is in the x. Then likewise, if the electric field in the x component is 0, then everything is in the y. So yeah, this gives you a nice description of horizontal and vertical. Now, slightly more complicated if you from that ellipse equation. Let's say the amplitudes, for convenience, I assume to be equal. Let's say the phase difference between x and y happens to be 0 or pi. You can plug it into your sine and cosine functions. Then you find that you can get this weird expression where you now have additional plus minus 2 on top of your circular part. So what you have is that ultimately you can basically show your EX and your EY, they're just can be EX equals to EY or EX equals to negative EY. So that means when your electric field is positive in X direction, it can be negative in the Y direction, for instance. And basically, it's something like that. So in a sense, I was just shaking the rope sideways or at an angle. So basically what this gives you is like what they call linear polarizations, because they all wiggle in a very nice distinct line and not in some weird ellipse or circle as you might have seen before. So you have a diagonal, anti-diagonal, just from definition here. Then there is another interesting case whereby you saw that Sheikh was able to make some cool little circles and other shapes. So things that if you set your phase difference to pi over 2 or 3 pi over 2, you can see that you get this very familiar equation again. Okay, everyone knows circle, right? Okay. So basically you have polarization that looks something like that, whereby the rope was kind of like going in this weird circular motion as it arrived to me. So it can basically have, from my point of view, I can say that it can be right circular or left circular depending on its direction. Or you can say clockwise, counterclockwise. But when you want to make abbreviations, right and left have R and L, clockwise and counterclockwise will start with C, so that makes it very hard. So now you want to express operations that change polarizations, and maybe squashing and stretching an ellipse is a bit complicated. So we move on to Jones. No prizes for guessing what this person's name was, but his idea was just very simple. So since light is propagating in the z direction, I don't have to care about the z component at all. Then all the electric fields that I'm concerned with are oscillating either in the x or y direction. So okay, great. Let me just put the expressions for ex and ey into this nice little stack. And then I can just just say, okay, some amplitude ax or ay, and then ei phi is just your, wait, you've gone through the Euler's expression, right, for exponential at the power of imaginary number, and then, yeah, so it's really just some sine and cosine. So just to describe the oscillating component. And so it just says okay, I can just do this, and I get this really nice vector. I can normalize it, and yeah, I get this nice little vector that will describe polarizations just based on the electric field in the x and y directions. Okay, so another note on normalization. I think Peter will have talked about this before. So does everyone agree that it's all the same? Okay, does everyone agree that these three vectors that I've written down, are they equal or are they the same? Okay, yes. The correct answer, if you ask the mathematicians, they'll tell you no, this is not the same.
It's different direction, but same magnitude.
In no sense, yes, but the thing is that so this is the part where it gets a bit confusing. Some will call this an abuse of notation. And in physics, we do this all the time because it makes life easier. We don't want to come up with a new symbol apart from equals. Anyway, so the whole idea is that if I normalize it, yeah. So as Peter mentioned about the whole idea of global phase just now, right? So the thing is that, as you said, they're all the same. I just have a different multiplicative constant. In this case, it is 1, 1. This one, I just see I is on both the top and the bottom. I can pull out the I, throw it away. This one is -1 and -1. I can pull out a -1 from both of them and throw it away. In the context of polarization, right, what it means is that I don't care how far they are from the start point. The more important information is how far apart they are from each other, or in this case, in terms of phase. So everyone okay with that? So yes, slight abuse of notation. The mathematicians will not like it if you tell them this, but it makes life easier for us, so we'll work with it. Okay, so in his formalism, when Jones was working on this, he said, okay, so say Ey goes to 0, then my bottom component here is 0, I normalize it, and hey, look, I get a 1, 0. Just that all my electric field just happens to be oscillating in the x direction. Likewise, if you have Ex equals to 0, then everything oscillates in the y and you get 0, 1. And so for the diagonal and anti-diagonal examples, you can just basically plug in the appropriate numbers where Ex equals to plus minus Ey and Ax equals to plus minus Ax. So it just shows that one either oscillates in phase or slightly out of phase. And you can basically end up with your vector of 1 over square root 2, 1 and plus minus 1, depending on which one you're going to call diagonal or anti-diagonal. Then additionally, you'll see that, okay, if you now have your imaginary number I to indicate the phase shift of pi over 2 or 3 pi over 2, you can work this out, and you see that you get 1 plus minus I for your right left circular polarizations. Everyone following okay so far? That's not a good sign. Okay, am I going a bit too fast, or everyone following the derivation all right so far? Yep.
Maybe you can summarize like the abstract idea of what you're going to do here, which from my understanding seems to be showing how you can map the theoretical idea of a qubit to.
Oh, we're getting there actually. It's just that for the description of polarization, it's just like rather than having to draw out a shape every time I tell you what polarization is coming at you, it's just like I just give you like a vector that has like 2 numbers, and I can tell and you can describe what polarization it is. So it's much simpler to work with compared to having to draw a new shape every time. Okay. So the thing is that with Jones' formalism is that he found it quite easy and convenient because, okay, if I have something that changes the polarization, I can just come up with what they call a Jones matrix. In this case, I indicated by T. Then E is this vector xy. So like if this vector representing polarization is being acted on by a particular optical component I have in the lab, I can just describe the transformation as just a matrix times a vector. Great, this is so much better than having to draw new shapes every time. And so just, you will have this for reference later, but it's just that for various components, which I'll talk about later, is that you have many common matrices. So the thing is that you don't always have to memorize everything. Sometimes you just Google and then you just like, what is the Jones matrix for this component? And then, okay, copy and you just write it down and you work it out yourself. Yes, use your resources wisely. And I'm hoping that you will start seeing something a bit familiar about all these matrices and vectors I'm writing down. You know, hint, previous lecture, really look like something yet. Wait, what?
Like, show them this like.
I'm not too sure, but okay.
What does it remind you of? What did we learn last lecture?
Okay, yes, okay,
Operator,
yep.
operator.
Okay, then going back again, like, what do all these like vectors look like? I mean, there's a pretty obvious. Yes, okay, but comparing, like, bringing it to say Peter's previous lecture.
I hear it.
Sorry. Oh yes, you can. Yeah, start to resemble like he is drawn like, let's say his cat state for what he calls cat 0 is just like a 1 0. Cat 1 can be a 0 1. So it's like, okay, you're starting to see that there is a particular similarity in how the notation has been built up here. Although in a sense, this notation was built to help, describe polarization and the changes you can effect on polarizations. Now you start to see that it looks quite similar to all the stuff that Peter has been talking about in the previous lecture. So yes, direct mappings. So your H, in this case, what he called a computational basis of like in 0 and 1, I can just call H and D, for instance. Then likewise, if it's for plus and minus, I can call it D and A. And then for his other stuff, we can show that with regards to superposition. So now you can think of it in terms of like how I combine polarization, so to speak. So for example, if I choose the D basis, I can see that, yeah, it's some combination of H and D. Maybe it's easier to draw it out. Where's the custard? It's always goes missing. Okay, so just as a recall from basic mathematics in Cartesian, let's say you have an X and a Y axis, then you can define something in between. You can call it some other axis, like maybe X prime. And you can say that, okay, like this vector that goes in the direction of X prime is some combination of X plus Y. So similar idea or similar logic for that polarization thing. So again, you can see that for the superposition part, it's that I can show that D is just some H plus V, and then if you choose a different basis, if let's say I don't like H and V, I want to work in D and A instead, then I can say, okay, yeah, you can. And now H is now in the superposition, I work in the basis of D and A. Make sense for everybody? Okay, so for instance, I can say like I want to work, you can work in XY basis, whereas if you rotate your head slightly, you may prefer X prime and Y prime instead, for instance. So things like just pure basis and you can define the superpositions in it. Everyone all right? Okay, so for circular basis, this is just a fun little exercise just to help engage you a bit more. Try to solve for A, B, C, and D. Did I put the answer in the lecture notes? Okay, for those who really want to recall what the R and L are, yeah, so R and L basically can be square one over square root of 2, 1, then plus minus, like, then which one you want to call R, which one you want to call L. Everyone okay with the R and L? Okay, sorry. No, as you know, to make sure I got consistent with my rotation. Everyone doing okay? So just for interest of time, this solution should look something like this. Yep. Okay, so yes, there is an I and minus I in the result. Or at least there should be an imaginary term somewhere, just because, well, your R and L are defined with the I, so the I has to appear somewhere ultimately. Everyone okay with the logic here? Okay, so Okay, so slightly more annoying problem. The thing is that just to show that any basis works. So it's in a sense your polarization is what is called an overcomplete system, whereby you are working in like technically like a two-dimensional space, right? You only need like two eigenvectors to describe the entire space. But in this case, I have 6. So like I have definitely a lot more than what I need. So things that you can have basically pairs of these eigenvectors, so H and V, D and A, R and L. And basically I can just pick my favorite and describe the other 4 as some combination of those two. So this probably be the most slightly more challenging one, whereby it's like, okay, let's say for some reason I love R and L, which I find very weird, but then you can say that, okay, H and V is now some weird superposition of R and L. So in this case, try solving. Okay, everyone okay? All right, so just time, just bring you the solution. Okay, so just a quick note on the discussion. Basically, some may find that you don't exactly have 0, 1, you have 0 and then I is at the bottom over here. So for that, please recall the point of normalization and a slight abuse of notation. So in a sense, 0, 1 is the same as 0 times I, because the whole global phase thing. In the sense that the vector here, as is for least for the Jones formalism, the goal is to describe polarization in terms of how the electric fields in X and Y are related to each other. So in a sense, you need to know their, in a sense, relative. I don't need to know how far they've traveled from, say, the laser I turned on or something else. Is the more important piece of information is how they are relative to each other. Like in a sense, if it's like, say, a sprint or a race, I don't care how far the two people have run. I just want to know how far apart they are from each other. I hope that helps. Okay, is everyone comfortable or any questions at this point? Because I know the math can be a bit unsettling and mathematicians will not like you if you tell them anything I told you here, but okay, no one has mathematicians for friends. Awesome. Okay, so this is the slightly more practical part, or at least practical in the lab, whereby I can now describe polarizations and all sorts of Fourier transformations. And now you go to the lab and like, okay, I need to actually do something with these polarizations. So how am I going to do it? So everyone, I assume, is familiar with this thing called a polarizer or linear polarizer. You might have seen it as some kind of sheets, black little sheets. You rotate it on some light source, and hey, the light is appearing, disappearing. So the whole idea is just very simple in the sense that based on the material properties, you have some axis of transmission. So if light happens to be oscillating or wiggling along this axis, it gets transmitted pretty well. Okay, so if it wiggles in an orthogonal direction, then well, it's not getting through, ideally. So this is also an important thing called Malus's law, whereby basically if you have this well-defined polarization with intensity or power, I naught, and then you're letting it go through another polarizer at a particular angle from the transmitting axis, then the power transmitted also gets reduced. Everyone okay with that? So practically, you have a slight problem if you only have linear polarizers to work with in your lab. So for example, if let's say I have, for example, this vertical polarization coming in, then let's say I want to change this to something horizontal. And now you have a problem, right? Because if you were to use a single polarizer, then like, okay, you've just been relying on one polarizer alone, you realize that, okay, if I want to get horizontal from this vertical, I need to rotate it like about 90 degrees, which means that I transmitted power basically becomes 0. And that's a headache, isn't it? Okay, everyone see the problem? Of if you have only polarizers to work with. Okay, just remember that the fun example given by someone last year is that, okay, you can have an infinite stack of polarizers, each one at a very slight theta from each other, and you can slowly transform that vertical to horizontal, which in principle can work, but the thing is, you're going to spend a lot of money to get those polarizers, a lot of them, and you have a super thick stack, which is also not very practical. So we look to a slightly different type of material. So I'm assuming everyone has okay, probably has not heard of the term birefringence. Okay, I'll take that as a no. So basically, there are particular materials that are called birefringent in the sense that different polarizations or orthogonal polarizations will interact with them differently, or that different polarizations will see different reflective indices. So in the sense, you have the transmitted ray that goes through without any bending or change in path. You just call it the ordinary ray, and there's a typo over here. This is the extraordinary ray, which is E ray. So in this case, you have the red horizontal and the green vertical polarizations. As they can enter this material and they come out, one is that there's a path split, and second is that each path now only has one particular polarization. So you might think that this is weird, you have to manufacture it, but it's actually a naturally occurring materials, like for example, calcite. So just somewhere you can rip off Google images. Where, for example, if you look at this pencil through it, so your ordinary ray is this one where you see the pencil. The extraordinary ray is this particular image that doesn't correspond to like anything directly underneath it. So the key idea is that you can affect two orthogonal polarizations differently. Each of them seeing a different refractive index, each of them can be delayed differently. So you recall that you want to add some polarizations to each other. I want to, in a sense, change from one state to another without killing it. So there's another method, what they call phase retardation, or basically just controlling the relative lag. So basically your wave, so basically you're just, in a sense, delaying one wave relative to the other. Lambda is just your wavelength. Wavelength is just like, for say, from one crest to the next crest, that distance. So things that you can basically use these components to introduce different degrees of delay. Everyone all right? So one important factor is that the angle at which you align its optical axis will also affect. So in a sense, if you angle it right, in this case, your input polarization may be horizontal. So you can have a wave plate that basically says you can rotate this now to a vertical. Everyone all right? How do I explain this better? Okay, so maybe another way to put this is that if you are looking at the optical axis of this particular wave plate, you're saying that the basis is now defined by this, at least for this component, defined by some optical axis. So the thing is that anything relative to it, or polarization relative to it, will experience different phase delays, and then you sum them up at the output, you get a different polarization. Everyone okay? So the thing is that you have now a larger library of materials to play around with. So you still have your polarizers, they're important. Then things that usually what we have are called half-wave plates and quarter-wave plates. Half-wave plate meaning that I introduce a relative delay in X and Y, for example, by half a wavelength. And then the other one is I delay it by, like say, 1/4 of a wavelength. Although some immediate limitations you may realize are that this is a bit of a wavelength dependent thing, whereby your wavelengths are different, you get slightly different delays, so you probably have to tailor your parts according to it. So things that your quarter-wave plates are in generally how we try to get like circular polarizations, where you have something that's linear, then I can basically use a quarter-wave plate to get a circular polarization out of it. Because quarter-wave plate meaning your quarter-wave delay, meaning you introduce a delay of pi over 2 or 3 pi over 2, which is where your I and your negative I appears. Okay, everyone okay? So know what's a quarter-wave plate, a half-wave plate, what they do?
Wait, you said that the refractive index based on like the direction of the wave. So that means that they can, for different like orientations of the original polarization, the wave can have, the material can have different refractive index.
For different polarizations, yes. The thing is that, okay, you may want to consult the material scientists, but usually it's from some regular crystals. Hold on, I don't need it. So in general, right, when you arrange in a crystal, let's just say that these little circles are like the particles that you arrange in the crystalline lattice. So let's say I have something like this, then things that you can stack them up, something like this. So just as an example, for example, if you were to come like at it this way, imagine it's just like a bunch of trees, right? You run it this way, you find that okay, this is pretty broad, you have a lot of space to squeeze through. But if you were to come in from this way, you realize that that's a bit of a problem. You may find this a bit squeezier. So in a sense, it depends on the arrangement of the crystal and how they are stacked up in a sense. So yes, the not so easy answer is that solve Maxwell's equations for this crystal structure, which is never trivial.
Isn't polarization not changing the direction of entry, but rather like the direction which it oscillates?
Right. The sense is the oscillation direction.
So in this case, basically it's going like if it oscillates like this way, it's like it gets slowed more because it's more likely to hit the path of gold as compared to like say if it oscillates like in and out of the thing. Is that like what you're trying to say?
Yeah, that was the thing. Wow. Okay. I have to put this. Sorry, this one is a very tricky metaphor to work with at the moment. When you say in and out of the plane, as in
taking this as a thing, since you're talking about
okay. So in a sense, you want me to orient the crystal differently, or
so as in what you're saying, like if like I'm just seeing if I understand is that like if it oscillates like say like this way, like there's less obstruction as compared to this way, based on what you've done.
obstruction? Yes, you could view it as a form of obstruction, recognize it as a form of obstruction in terms of how it's slowed down.
So that's how the speed varies.
Right. So it just depends on how the little or atoms or molecules are arranged within the crystal lattice itself. For more on this, solid state physics. Okay, so next problem is just a very simple one in the lab. So you may have talked from Peter's lecture, like, okay, people send you different states, different stuff. And like you say, okay, you want to make measurements. So the problem is that if I send you a photon, and then it's like say, you don't know what state this photon is in. So the problem is, how many measurements do you need to make before you can give a conclusive answer as to what state it is in? Anyone want to guess the number? So you think of it in terms of just say that you don't know the polarization of the incoming photon. Like how many measurements do you need to make in order for you to definitively tell me that I know what the polarization state it's in? Okay, any other random guesses? I heard 1, there's 3, some say 4. Oh, I mean 15, yeah, a bit overkill, but I don't think I could do it 15. Okay, yes. In general, yes. The more measurements, the better. Your error kind of goes down. But the thing is that, you know, you're a PhD student. You've got only so many years before you have to graduate. So you can't spend all like 4 years just taking measurements of one system over and over again. 2. Okay. Slightly more than 1. A bit much. Okay, okay. Let me just tell you. So the basically, practically speaking, right, you need 4 measurements. So there's one key problem here that I think, or key assumption that usually made, is that when you're measuring the state of a particular system, right, the inherent assumption is that you have infinite copies of this state that you can keep measuring over and over and over again, such that you can get probabilities and statistics. But the thing is that if you only have 1 photon, I only give you 1 photon. How many measurements can you make of 1 photon before it's gone? Come on, it's an integer. It's a pretty small number. Okay, how many measurements? If I give you 1 photon, right? How many measurements can you make on it before it's gone? Yeah, at most 1. So that's an issue. So things that you need multiple copies, or at least the inherent assumption when you say that I make measurements of like a particular state is that you have tons of copies of that state. So in terms of polarization, in fact, we need 4, like the bare minimum is 4 measurements to be sure. So it says that I need, if you give me a photon, I tell you like, I'll just tell you, I need at least 3 more if you want me to give a conclusive measurement on what polarization it's in. So basically, one is just I have a polarizer at 0 degrees, 1 at 90 degrees, polarizer at 45, and I have a polarizer plus a quarter wave plate. The interpretation of this thing is just that the first term just gives you the total power. This is just a normalization term. Then basically your first term S1 in this Stokes vector is just basically how much more horizontal than vertical it is. So the power in the horizontal minus the power in the vertical. The second, sorry, S2 basically just means how much more diagonal than anti-diagonal it is. Then basically S3 just tells you like how circular, how right circular compared to how left circular it is. So then all these values, if you normalize, should range from basically 1 to -1. So this is just the practical one you work with. So if you want to like write your polarization vectors in this particular formalism, the first term is always 1, just to assume it's normalized, then you have all these other terms. Yeah, it's really open Peter about it. But anyway, so things that what you can do is that I can plot S1, S2, and S3 as like a 3 axes, and we can form a sphere. So things that at each of the ends of the sphere, so for example, let's say if S1 equals to 1, then okay, this thing is perfectly horizontally linear. Then if S1 equals to -1, I have something that's vertically linear. So do you guys recall what Nigel was telling you about plus C, minus C and all that? Right, so in his spin states, plus C and minus C are different. Whereas you see, right, for H and V, right, they're basically like orthogonal. One is horizontal, the other is vertical. They're basically like 90 degrees apart physically. But then if you plot it in this space, right, you realize that, for example, this is horizontal over here when S1 equals to +1. Then vertical is over here, where S1 is -1. Now do you start to see the similarities? Okay, so this is what they call a Poincare sphere to map out all possible polarizations. And basically, if I can map out the spin systems as well, this would basically be your block sphere as well. So in the sense, the Poincare sphere used to describe polarizations has a one-to-one mapping to a block sphere, which describes qubits. Hence, you see that the polarization property of light itself can basically be used as a qubit. Everyone okay? That's a pretty big conclusion I'm trying to make here. Then just to go back to the whole point of the weird shapes and the ellipse, right? So things that it can also map onto this sphere, basically just saying that this is a more convenient representation. Like the orientation angle, the ellipticity angle, basically they just map onto the sphere in this particular way. And also the other point is that normally for Stokes vectors, we just work with S1, S2, S3, since the last term or first term, depending on how you order it, S0, is just for normalization purposes only. It's just to guarantee that the vector is contained within the sphere, i.e. it only has length maximum of 1. So slight subtlety is that there's this thing called a degree of polarization, because things that your vector length is less than 1. For example, if it's just sunlight, you have basically unpolarized light. It means that it will be sitting somewhere nicely at the center. Basically, it means that your degree of polarization is 0. So basically, if you take your four measurements, basically it's like, the powers are basically about the same. So each one minus the other gives you 0. Okay, so just as a quick to sum up everything, it's like, are the Jones vectors and the Stokes vectors basically the same, or are they different, or they just make them up somehow?
The same but different context.
Okay, can you elaborate on that? When you say same but different context?
I think the Jones vectors looks like more of a cool. I think because there's these two like vector numbers dimension. I think, but like the constant looks like a 3D. I guess that's different, but I don't know.
Guys, so basically for your Stokes and Jones vectors, they are technically similar, but things that your Jones vectors only apply if you're on the surface of the sphere, i.e. your degree of polarization is exactly 1. Whereas your Stokes vectors are more general, in the sense that they apply to anything within the sphere and on the surface of the sphere. Everyone okay? So in a sense, if you give me a Jones vector, I can tell you what Stokes vector it corresponds to. But if I give you a random Stokes vector, you may or may not be able to get a Jones vector out of it. Everyone all right? Okay, and that's why I wanted to cover polarization and optical qubits. If you have any questions, you can just ask away now before you go for lunch.